So far we've gotten a kind of a sneak peek into the way that the periodic table is organized. And real quick, I'm just going to pull up a copy of that here. Okay, and as we pointed out earlier, um, for the symbol of each, for each entry on the periodic table for each element, there is a number that's given that represents the atomic number. And that's the number of protons that are in the nucleus of that atom. So we said hydrogen was 1, helium was 2, and then lithium was 3, and so on. Okay, again, you can see here that the periodic table is at least organized according to increasing atomic number as you go from left to right and from top to the bottom. But there's other degrees of organization on the periodic table as well. And hopefully you're going to find through this course over time that this periodic table is more than just some wall art. It's more than just a listing of the elements, but rather a tool that allows us to understand how the elements actually work. Okay, now one way that's particularly helpful, and well, one way that it's organized that's particularly helpful, has to do with the properties of the atoms of each one of these elements. And we can essentially break up this entire periodic table into 3 units. Okay, one unit is going to include all this stuff here. Okay, all the way, let's see here, there, down to there, and all the way across here. Okay, everything that's enclosed in that blue box that I just drew there is what we call metals, or are called metals, I should say. Okay, and metals are elements that tend to be shiny. Okay, they tend to be malleable, which means you can hit them with a hammer. They're not going to shatter. They will bend. Okay, and they tend to be good conductors of electricity. Okay, and this is generally true of all the things that I've highlighted here. Now, over here, we have this little stair-step region. Okay, that includes all of these elements here. Okay, and whether or not we can include these elements down here is really dependent upon whether or not we have enough of that stuff to actually experiment on them. And then everything to the right of that okay, is what we call nonmetals. Okay, and nonmetals tend to be dull or colorless. They tend to be brittle, so if you were to hit them with a hammer, they wouldn't bend, they would just shatter. And they tend not to be very good conductors of electricity, so I'm going to call them insulators. Okay, which leaves us with that little stair-step region there. And these are what we call the metalloids. Okay, and the metalloids are elements that kind of fall in between the properties of the metals and the nonmetals. And one of the most notable behaviors is their ability to kind of partially conduct electricity, depending upon how they're treated and how they're manufactured. Things that contain these metals can either conduct electricity or not conduct electricity, which is why they're used so prominently in microchip technology. Now, when we're talking about elements, some elements exist as single atoms. So in other words, they're discrete atoms that are just being packed together in some way. These are called monatomic elements. Okay, and these are going to be things like the noble gases, things like xenon or neon, helium, okay, or krypton. Okay, but some elements actually exist as molecules. And a molecule occurs whenever you have two or more atoms being stuck together through what we call chemical bonds. Okay, and there's a number of elements that that exist diatomically. Okay, we call these the diatomic elements. Okay, and these would be hydrogen. So you never see a hydrogen atom by itself. If you have elemental hydrogen, you have basically a big collection of H2. Okay, the same thing goes for nitrogen and oxygen, and then the halogens, fluorine, chlorine, bromine, and iodine. Now these are all examples of diatomic elements, but we can have diatomic molecules that are composed of elements that are not the same. Okay, so we can have things like HCl, okay, or HBr, or NO, okay, just as an example there. And then by far the majority of compounds out there are polyatomic molecules. Okay, of course, meaning many atoms, so anything more than two. Okay, these are going to be things like H2O. Notice there's two elements, but there's three atoms. Or NH3, or something like glucose, which would be C6H12O6. Okay, so that's examples of monatomic, diatomic, and polyatomic. Now, there are some compounds that exist that do not form molecules. Okay, so the atoms are being held together not necessarily by these chemical bonds. Well, they're still chemical bonds, but it's more of a plus minus attraction. Okay, kind of imagining the two poles of different magnets being attracted to one another. Okay, so for example, you could have something like sodium with a positive charge run into something like chloride, which is chlorine with a negative charge, to make NaCl. Okay, so we say that the sodium in this case, because it has a positive charge, is a cation. Okay, the chloride we call an anion because it has a negative charge. Okay, and both of these things are types of ions. And the compound that's produced is an ionic compound. Okay, now at this point you're probably wondering, well, why is it that the sodium takes on a positive charge? Or chloride, why does it take on that negative charge? And that's something that we will address in Chapter 8. There's actually a very good explanation for that. But there are some elements that tend to form cations, some that form anions. And actually, metals tend to form cations, while nonmetals tend to form anions.